and ongoing work as well, which is recent glaciation on Mars. And as Toby said, I'm currently a bit of a Martian on Earth, in that last year I finished my PhD at the OU down in Milton Keynes, studying wet-based glaciation on Mars. And I'd come down to Earth for a few years to work on this fantastic project with Chris Clark and the PalGlac team here in Sheffield, reconstructing the dynamics of the Scandinavian ice sheet. We're a big team, as you can see here. This is just the Sheffield contingent plus one from Manchester, Anna Hughes. And we're working hard, but that's still early days. So today I'm going to be talking to you about my Martian work, which we've got lots of fun science to talk to you about. So all this work would not have been possible without several people. These are just a few of them. The top row of this image, I wanted to thank in particular because pretty much all of those people were involved, whether formally or otherwise, in supervising my PhD work. And the bottom row are other collaborators, master students, and colleagues who have also contributed to this work. So thank you very much to them. This is very much a team effort, and I can't take sole credit for any of the stuff I'm going to present to you. So when you think of Mars, well, a lot of people, when they think of Mars, will think of the red planet, probably. It's not entirely red. There are a few blue splotches and also some bright white polar caps, but they will probably think of the red planet. And this is an image mosaic from the Viking spacecraft. This is all the way back in the 1970s. So this is a sort of common view of Mars, but if you say Mars to a planetary geomorphologist, they're more likely to think of this image, which is Mars's elevation. So it's a digital elevation model of Mars, a global one from the Mars Global Surveyor. This is the molar map of Mars, derived from laser altimetry. And this is the only global DEM we have at the moment. So at the equator, it is, I think, between 450 and 500 meters resolution. And at the poles, it's closer to 100 meters. So this is our global view of Mars. And this came out in the 1990s. So it's pretty impressive. And as you can see, it completely changed our sort of understanding and view of Mars. It turned it into Technicolor for us. And in this map, for example, you can see, I hope you can see my mouse, do shout if you can't. You can see Olympus Mons here, which is the biggest volcano in the solar system. It's about the size of France for an area comparison. Here is the famous Valles Marineris, which is a huge canyon in the equatorial regions, which would dwarf the Grand Canyon here on Earth. And this is Hellas Planitia, which is the largest visible impact basin in the solar system. And the other thing that might strike you is that we've got lots of red down here and lots of blue up here. Well, the blues are low and the reds are high. And this is basically the planetary dichotomy. So down here we have, in the south, we have a very ancient old cratered highlands, and down up in the northern lowlands, we have much younger surfaces, much smoother surfaces in this basin in the north. So that was the view provided by Mars Global Surveyor. But we do have a new generation of spacecraft at Mars now. Mars Global Surveyor sadly is no longer sending us data, but one of my particular favorites, and I hope this video will work for you, it might be a bit jittery, one of my particular favorites is the Mars Reconnaissance Orbiter, which carries two cameras on board. The first is the context camera, which has provided a 6-meter resolution global image mosaic of Mars, which you can actually see in Google Earth if you want to go and have a look. And it also provides 25 centimeter resolution images of parts of the surface, which we can use to create stereo-derived digital elevation models at 1 meter resolution. So yeah, it's pretty good. And we can do quite a lot of geomorphology with data of this fantastic quality. This is a video, shout out to Sean Duran, who is on Twitter as @the Shawning, I think that is. He produces these amazing fly-throughs using HiRISE data, which is entirely free for use by the general public and scientists alike. So the view that you just saw flying through, I might be able to reverse it again in case you missed it, is gullies, possible water carved gullies, but more likely in the present day CO2 carved gullies in an impact crater on Mars. So these are the kinds of stunning views that we get of Mars from the HiRISE instrument on the Mars Reconnaissance Orbiter, and a significant source of data for me for my work. So all of these data sets, that's just a small subset of them, we have plenty of data sets to use, have allowed us to build up a picture of Mars's geologic history. Now Mars doesn't have plate tectonics, which means that we don't have crustal recycling like we do on Earth. So that means that there's quite a significant geologic record preserved on its surface. So not only crustal recycling, but the fact that erosion rates are much lower on Mars means that we preserve a lot of information. So we can use that to start to build up an understanding of its geologic history. So my work is primarily focused in this period called the Amazonian, which has dominated Mars's geologic history from the present day right back to 3 billion years. Now, in Mars terms, we work on much longer timescales, but anything less than 1 billion years is considered recent on Mars, I would say. So the Amazonian is this big period here. Before that, we had the Hesperian, and before that, we had the Noachian. And then the base of the Noachian is defined by the Hellas impact basin, which I pointed out on that molar map. And from geologic studies of the surface of Mars, both from rovers and from satellites, we've been able to consider that Mars has probably changed over time from what was probably a close to habitable, if not habitable world, to microbes at least, back in the Noachian, and water flowed across its surface and left things like river channels, possibly even a northern ocean and lakes, but there's a bit of uncertainty about what the Noachian actually looked like, whether it was dominated by oceans or ice sheets, but there were certainly at least periodic periods of wetness, or transient periods of wetness, I should say, with a lot of water involved. And then over time, Mars is thought to have dried out and become more like the desert environment it is today, through the Hesperian and into the Amazonian, where now it's a kind of dry, frozen planet. So to contextualize, here are a few parameters for Mars to get you a bit oriented about what kind of environment at present. So in the present day, the sort of mean annual temperature at the equator is around 210 Kelvin, which is pretty chilly. But it can get up to a toasty 303 Kelvin at the equator at midday, but that's pretty unusual for most of the planet. And down at the poles, yeah, you really don't want to be there. It's extremely cold. It's less than 140 Kelvin in winter. So in terms of temperature, it's pretty cold. We also have significantly lower atmospheric pressure than we do on Earth. So Mars' atmospheric pressure on average is about 6 millibars. And as we all know, the gravity is much less than Earth as well. Now, the axial tilt in the present day is around 25 degrees, so relatively similar to Earth, but that has varied quite significantly over time. And recently it could have varied, or it's thought to have varied between about, and by recently, sorry, I should say that's probably about 20 million years, varied by 10 degrees either way. Actually up to 45 degrees and down to 15 degrees, so maybe 20 degrees higher than it is in the present day. And it's varied by 10 degrees either way over periods of about 100,000 years, so quite similar to Milankovitch cycles here on Earth. And as I'll explain later, that is thought to be the cause of non-polar glaciation on Mars, so the mobilization of ice from polar reservoirs down to the mid-latitudes and high latitudes of Mars is that obliquity variation, changes in the planetary tilt. So those parameters probably suggest you, and you would be correct in thinking that Mars is an icy world, and why would I be at a glaciology seminar if it wasn't? So you're probably aware that Mars has polar caps. So this is a view of the North Polar Cap, which is a thick deposit, up to 3 kilometers thick, I think, on Mars, and it's predominantly water ice. And the North and South Polar Caps of Mars combined probably contain about the same amount of water ice as the Greenland ice sheet. That's a bit of a comparison for you. So at the poles, the temperature is sufficiently low that it's below the sublimation point of ice at the surface of Mars. Now, there's no surface or perennial surface ice beyond the poles of Mars because of the atmospheric pressure. So the atmospheric pressure is very low, and that means that the temperature is above the sublimation point. So the distribution of ice on Mars isn't controlled by the melting point, it's controlled by the sublimation point. So the polar caps are really beautiful, but we do also have lesser known reservoirs of ice on Mars. So this is a view from the Phoenix lander, which landed on Mars, I think in 2007, maybe 2006. And it scraped into the regolith, so the soil of Mars, up in the high latitudes, in the northern high latitudes. And what it revealed was what was suspected, which is that just centimetres below the surface, we have these lenses of water ice stored within the surface. And if you can see on this panel here, between this view on one day, you see there's little white lumps here. And over the period of a few Martian days, they've disappeared. And there was no meltwater involved here. As I said, this is sublimation. So we've lost ice between here and here. So this is a significant reservoir of ice on Mars. So similar to ground ice here on Earth. And we don't just have to be on the ground to observe that, we can actually see it from space. So this here is a high-rise image of some polygonal ground. So this might look quite familiar compared to polygonal features in icy environments here on Earth. But the elephant in the room is that there's an impact crater in this polygonal terrain, and it has exhumed this bright water ice deposit, which proceeded to fade over, I think, a season or a couple of seasons. And then the right-hand view here is a recent discovery of almost, I think, more than 100-meter high cliff of water ice that's retreating in Mars high latitudes, and you can see it's covered in debris, but underneath we've got this bright cliff of water ice. So there's plenty of ice kicking around in the high latitudes of Mars. But now I'm going to bring you down to the mid-latitudes. So just to orient yourself, this is where that Phoenix lander was. So this is the trenches with the ice in it. But we're going to focus on the mid-latitudes, which is where all of these bright, horribly pink points are. Each of these points represents a glacier on Mars. So this database is a combination of glaciers compiled by Joe Levy and colleagues, and also by Colin Souness when he was a PhD student at Aberystwyth. And you can see there's thousands of them. There's plenty of glaciological work to be done on Mars. And as my title slide showed, this is what they look like. So again, shout out to Sean Duran for his amazing image processing work here. This is sort of a community favorite, this glacier. Actually, you can check out a recent paper by Adam Hepburn at Aberystwyth University, along with colleagues here in Sheffield. They published about this glacier, which is actually advancing out over the top of another glacier. So this is multiple stages of recurrent glaciation. This is one of the youngest type, well, probably the youngest type of mid-latitude glacier on Mars. This is a small valley glacier. But we also see much bigger features, such as the one that one's advancing out over. So this is kind of like what you call a Piedmont style glacier. It's not constrained by topography, and it's these aprons passing out into the plains here. And you can see the scale bar, this is 10 kilometers. So these are tens of kilometers long. We then have valley filling glaciers that are much bigger than that example I showed you before, but more like they can be up to hundreds of kilometers long in some cases, and they have these amazing flow patterns on their surfaces. So these are valley filling glaciers. And then a slightly unusual one for maybe an Earth perspective, but I'd say the most common type of glaciation on Mars is actually crater glaciation. So this is what we call a concentric crater fill, because we don't talk about genetic feature names on Mars, just in case we're wrong. But this is a glacier infilling a crater on Mars. So these are very common. So my research specifically has been looking to see if these glaciers have ever been wet-based, as my title suggested. Now, the reason my title said, is it stubborn cold-based glaciation or reluctant wet-based glaciation? is that the prevailing view is, given that these glaciers are probably between a few million years old in terms of the smaller ones, but also up to maybe a few 100 million years to a billion years for the bigger ones, which for Mars is very recent. They formed during the Amazonian period, which is this very cold, dry, hyperarid period. So it seems unlikely that there's been any big climate perturbations in that time, at least as far as we know. So it's sort of been thought that those glaciers have really done very much. They've just sort of advanced and then retreated by sublimation if they've undergone retreat. But we're pretty convinced that there's probably a more complex story to tell than just 3 billion years of dry, cold Mars. And I think our research is starting to show this. And this links back to the fact that Mars obliquity has been varying over timescales of 100,000 years very significantly. And so we've probably been mobilizing ice around the planet. And so what has that done to the climate and to other aspects of Mars's environment? And this is the kind of questions that we're asking. But generally, we do think that it's probably been pretty cold. So have extant glaciers on Mars ever been wet-based? Well, just before I started my PhD, my colleagues Coleman Gallagher at UCD in Ireland and Matt Baum, who was my lead PhD supervisor at the OU, discovered this system in the Phlegramontes region, which I'll point out here with this star. This is a mid-latitude location, and this is a valley occupying a tectonic graben. So this is a graben valley here. The glacier terminates here in the present day, and it has this very intriguing foreland, which from this view you can probably start to see some rather interesting features on it. But I want to draw your attention down here to this feature that's about, in the present day, 40 kilometers from the terminus of this glacier, which if I switch on to the next slide, you will probably have a look at this and think, that's an esker. I agree, that's an esker. And this is what Coleman and Matt found back in probably before 2015, but it was published in 2015. This was the first esker to be identified in association with a present-day glacier on Mars. And this indicates that that glacier underwent basal melting at some point in its history. That glacier was dated by impact crater counting, which if you have any questions about, feel free to ask at the end. But it was dated to around about 150 million years old in its present state. So it's probably a bit older than that because the glaciers had to retreat. But yeah, this is the first esker. And just in case you don't know, an esker is the infill of a glacial meltwater channel. So it's sedimentary infill carried by glacial meltwater through ice-walled tunnels. So, and I think it's a beautiful example. So hooray to Coleman and Matt for finding that. And then I came along, all enthusiastic as a first-year PhD student, and I loved eskers already. I'd studied ancient eskers at Mars South Pole as an undergraduate, so I was keen to find some more, and came pretty quickly, actually. Within a few weeks of starting my PhD, I'd just been scrolling around Mars, and I spotted this feature here, which is the second esker to be identified with a glacier on Mars. And this one isn't actually far out in front of its glacier, it's actually still partially buried. So downslope is up towards the top of the screen. It's just the best illumination for visualization. So in blue is its remnant parent glacier, which we've dated to around about 110 million years. It's a fair amount of uncertainty on that, but it's a similar ballpark to the Phlegramontes one at 150 million years. And it terminates at this dotted line, and in pink is the esker. So we've done a lot of work on this esker, and I'll show you a bit more later. But for now, the question that's probably in your head is, well, given that Mars has been really cold and really dry, or we think it has been, what on earth could have caused the melting episodes that formed these eskers? Now, we don't think there are eskers all over the place. These seem to be quite rare examples. So it doesn't seem likely that it's a big climate anomaly that's caused this, not a massive swing in climate, because then we would expect to see much more widespread evidence of wet-based glaciation. So we need some other explanation. And we think we've found a pretty good explanation. If it's not climate, it could be geothermal heat. And this seems to be supported by the geologic settings of these features. So these are the locations of the two Eskers I've shown you so far. This is Flegramontes, and this is where that glacier was in this graben. And you can see this graben system continues across here as well. So this is a big graben system. And then this is the one that I found in what's called the Temperatura region. So I should say on this map, the one I found is here, and the one that Common Map found is here. So they're sort of almost on opposite sides of the planet. And they're both located in tectonic rifts or graben, which we suggest could mean that geothermal heat could be the culprit for the melting of these glaciers. Now, we're not suggesting that the primary geothermal anomaly for the formation of these rifts or graben is responsible, because they're probably quite ancient. However, certainly in the case of Temperatura, we've found evidence of very recent faulting in this area. So there's some very fresh fault scarps down here, so fresh in fact that they're basically undateable. So we think it's, even though the sort of Mars's geothermal heyday is a long time ago, it seems likely that there could still be, or have recently been, some geothermal anomalies in the subsurface, that it didn't just die altogether. So potentially that is the source of heat, and that's what we've been investigating. So having looked at the geologic setting, my co-author and former PhD supervisor, Neil Arnold at the Scott Polar Research Institute, did some modelling on this to try and find out what kind of parameter space we're looking at for causing this melting to form these eskers. So Neil formed this 1D model, which was looking at the basal temperature at a single point on the bed of a glacier. And the first set of experiments that he ran considered the mean annual surface temperature, the thickness of the ice, and the geothermal heat flux. So a very simple scenario to start with. And I'm not going to bend your brain with this plot, but basically this is a cube of the parameter space. And the colours represent temperature. So up towards the top corner where it's yellow, we've got high geothermal heat flux, high ice thickness, high surface temperature, and down towards this corner we have lower of all of those values. And what this shows is that where geothermal heat is the only additional heat source, these are the conditions that we need to produce basal meltwater. So we need a mean annual surface temperature of about 215 Kelvin, which is a fair increase from the 190 Kelvin in the present day. At these latitudes, we need about 80 milliwatts per meter squared of geothermal heat flux, which is quite a lot higher than the present global average, although this is a modelled value. And it seems likely that if there have been variations on Mars, then it might have deviated quite significantly from this if there was any subsurface activity. But that's still quite a hike. And then we would need more than a kilometre's ice thickness. So even though these values aren't completely unrealistic, there's still quite a lot of change required to cause this melting. However, that model did not include strain heating. Now, strain heating has been sort of ignored for Mars because basically it's highly temperature dependent, and the thought is that, well, Mars is quite cold, the ice is very cold, so probably strain heating is negligible. However, as I said, it's highly temperature dependent. So if you have any increase in the temperature of the ice, for example, due to geothermal heat flux, the effect of that on strain heating is highly nonlinear. And that means that strain heating can help in this regard, particularly in the settings that we're looking at where ice is flowing convergently in steep-sided tectonic rifts, which seems consistent with our observations. So this is the model results that Neil produced when you incorporate strain heating. So on the right here, we have the first plot that I showed you. And on the left is not the basal temperature this time, it's actually a change in temperature from the right-hand condition. So up in the top corner, it was already at melting point, so we don't have any change in temperature. Down here, it's still too cold, so no change in temperature because strain heating is very temperature dependent. But at that threshold that I was talking about, we get quite a significant heating effect. So what this shows is that for 100 kilopascal driving stress, and we did do, Neil did do other scenarios as well of 20 and 70 kilopascals of driving stress. We get up to 15 Kelvin of additional heating just from the strain heating. And that basically means that the conditions we need aren't quite as different from what we might expect. So now we only need 205 Kelvin of mean annual surface temperature, more than 50 milliwatts of geothermal heat flux. Now that is similar to the maximum modelled geothermal heat flux for the present day. So it's possible that in the past we've got similar values like that. And then the ice thickness required is also reduced as well to about 900 meters, and that's quite consistent with our understanding of ice loss on Mars, and also with the depth of the valleys that the glaciers are infilling. So yeah, these are the thresholds that we might need for the production of Eskers. So this is the start of some of modelling work that we want to continue. So this is obviously a 1D model, but hopefully in the future, well, kind of underway, but still in progress, is 3D modelling experiments to test this further. Okay, so third question. Now that we know a bit about the environment, what can we learn specifically about the Esker forming meltwater events themselves? Well, we're taking a three-pronged approach to this. I'm quite fond of morphometrics, so I've been doing a lot of morphometric analyses of Eskers on Mars. We're also doing some Esker sedimentation modelling to combine those morphometric analyses with some understanding of the parameters required for Esker sedimentation and what different Mars parameters does to Esker sedimentation. And also critically, and something that's very important, is terrestrial analogue studies. We can't study Mars in isolation from Earth, and this is something that I am quite resolute on. I think it's extremely important to consider both planets together. And so in terms of the morphometric analyses, what am I trying to achieve? Well, I want to probe the Esker forming processes themselves, but also consider the implications for potential Eskers we might find elsewhere on Mars. So we're building a comparative database of the morphometries of Eskers on both Mars and Earth. And this is both to compare between meltwater events, so the different Eskers forming in different locations, what are the similarities, what are the differences, what could that mean for variations in meltwater dynamics and things like that. But also, it will help us to find Eskers elsewhere on Mars, because basically there's a lot of processes on Mars that form sinuous ridge landforms. So this is what we call them when we first see something that looks a bit like an Esker. We call it a sinuous ridge because we need to prove it's an Esker. And there are a lot of sinuous ridges on Mars, but not all of them are Eskers. And so having a morphometric database where we can look for morphometric signatures of Eskers is really important, particularly when we can't just go and hit things with hammers, which is obviously quite an important technique here on Earth. And I mean, we're limited by what we can do in terms of ground-based studies on Mars at the moment, obviously. So we're doing our very best, but this is another reason why it cannot be studied in isolation from Earth. And just a sneak peek at a new paper that came out just a few weeks ago of a morphometric study of the Esker that I found in Tempe Terra. This is a system where we think the morphometrics show us that there's actually some quite interesting variations in potentially the dynamics of the subglacial drainage that formed it, both in space and time. So I won't go into details because I know it's late at night or early in the morning for a lot of people, but this is basically an idea of what we've found. We've done some detailed morphometric analysis that shows that actually there seems to be potentially an Esker ridge sitting on top of an Esker ridge. So potentially two phases of meltwater drainage at least to form this Esker, and potentially some implications therefore for the dynamics of subglacial drainage. So do check out that paper if you're interested. I'm quite keen to hear anybody's feedback on that because I know it's pushing the boundaries a little bit. So yeah, that's one site where we've published the morphometrics specifically for. And we're also studying these in combination with Eskers on Earth. And shout out to Rob Storer at Sheffield Hallam and also Andrew Jones, who have been compiling Esker morphometries for Earth and have now teamed up with members of the PowerBlack project here at Sheffield University to look at the morphometries of Eskers on Earth. So Rob in a map of Eskers in Canada, and in 2014 followed up with a study of the 2D morphometrics of those ridges, so things like length, sinuosity, continuity, or degree of fragmentation. And now we're working on this 3D database, which is going to be really valuable for comparing to Eskers on Mars and understanding the similarities and also the differences between them. So a bit of a sneak peek at some of the comparisons we've been doing. This is at the moment just for the 2 sites that I've spoken about today. So the 2 sites on Mars, split down into their crest morphology. So Eskers on Mars, Eskers anywhere, have crest morphology variations that may be associated with the process of formation. So the colours are the crest morphology. You can see site 1 here, site 2, site 1, site 2. And so the coloured ones are Mars and the grey one is Finland. And you can see that just from this sort of preliminary comparison, sharp crested ones, so triangular shaped portions of the ridge, have for the 2 sites on Mars very similar heights and widths, despite the fact they're on opposite sides of the planet. Sorry, very similar heights, despite the fact they're on opposite sides of the planet. And for the sort of round crested sections, we have actually quite different heights and widths between the 2 sites. However, when we compare the ratio of the heights and widths, we see that for the round crested portions, the relationship between height and width, despite significant absolute differences in those values, the ratio between them is quite similar. So this maybe points preliminarily to some kind of process relationship between width and height of these Eskers, and potentially some similarities in the sort of dynamics of the meltwater events that formed them. But obviously this is work in progress. Now, some of you might have spotted that the width-height ratio here for the Eskers on Mars is towards the upper bounds of the Eskers measured in Finland. This is consistent with observations of both these Eskers and also ancient Eskers on Mars. Eskers on Mars seem to be wider than Eskers on Earth, basically, and we think we might have a process explanation for that from the Esker sedimentation modelling, but watch this space for that. So we think we can explain that without them not being Eskers, if that makes sense. So we've got the process implications, potentially. Now, for the other question, did it happen anywhere else? So we've got these 2 sites for where we found Eskers associated with glaciers, but did recent wet-based glaciation occur anywhere else on Mars? So we focused down on those 2 sites, but now I'm sort of coming back and looking at the bigger picture and looking for evidence elsewhere. So we are actively searching several regions on Mars. So I myself am quite focused on the Temperatura region, which is where I found that second Esker, so that's up here in this rift up here. But we have found several other sinuous ridges associated with glaciers in this region. And we're working alongside Andreas Johnson in Sweden on this, who's also found plenty of them in this region. And so this is the rift that I've mapped already with the Esker. But I'm working with a master's student here in Sheffield, Savannah, who's mapping this area, where we have 2 other candidate Eskers associated with glaciers. So Savannah's mapping the land system and also doing some morphometrics of the ridges. So potentially we've actually got a sort of spine of wet-based glaciation down here, but we're still testing whether these are Eskers. And then over here is an impact crater that is extremely interesting in my opinion. And you'll see that it's still in the same physiographic region as the ones that I've already been talking about, which is actually a massive volcano-tectonic province. So there's this huge rift system passing through here, again, potentially consistent with this hypothesis that geothermal heating is required for wet-based glaciation. And so this is Chukung crater. Some of you will recognise the name Chukung as a village in Nepal. So I named this crater thanks to a suggestion from Katie Martin Evan Miles of the Everdrill team. And the reason this is called Chukung crater is because of the debris-covered glaciers within it. I don't think I've actually said yet, I probably should have done, that we think that the glaciers in Mars mid-latitude are debris covered. Then they're not bright white, so they're not exposed ice, and they can't exist as exposed ice because of this sublimation problem. Radar evidence has shown that they are probably near pure ice, but they probably have a covering of about 10 meters of debris on top. So apologies, I should have said that earlier. So Chucken Crater is interesting because it has debris covered glaciers. You might be able to see these lobes in the south of the crater here. And if I zoom in, if I actually map I've made, so this has just been submitted to Icarus. This shows in sort of more clear detail that we have a ice here down in the southern Chucken Crater, and then some interesting stuff going on up here in the north as well, including what we think are more ancient fluvial valleys. So if we now zoom in, I promise, we can see that Chucken Crater hosts a very diverse array of sinuous ridges. And this is something that I'm also working with another master's student on, Aaron Wild, here in Sheffield, who's doing morphometric analyses of these ridges to sort of probe further their origins. We think that some of these could be Eskers. We don't think that all of them are Eskers. So there's sinuous ridges in northern Chucken Crater, if I go back a second, up here, that are associated with fluvial valleys that we think are something called inverted paleochannels. So they are exhumed fluvial ridges from pre-glacial times, and they're quite common features on Mars from ancient Mars processes. So we think that they're inverted paleochannels, but some of the ridges emerge from glaciers and are very Esker-like. So this, for example, we think is very Esker-like, and here's another candidate Esker here. And here is actually a candidate inverted paleochannel, so one of those fluvial ridges superposed by what could be an Esker. And there's, apart from them just being these sort of sharp-crested, look a bit like Eskers things, there are several reasons why we think they could be Eskers. Firstly, they emerged from these massive glacier complexes, so these are potentially hummocky moraines. Here, these smooth bits are the sort of remnant glacial deposits. They're sitting within valleys, which I should say we think are probably pre-glacial fluvial valleys. We don't think they are meltwater valleys, but they don't necessarily follow the axes of those valleys. So this image on the right-hand side is zoom in of panel B here, and you can see that we have this valley floor ridge, but also a ridge that ascends the valley side quite significantly. So this valley side is tens of meters high, I think possibly 30 meters high, the ridge itself only about 5 meters high, and they ascend these valley walls, which is very Esker-like because Eskers don't necessarily follow the steepest topographic slope. The hydraulic potential gradient is modified by the overlying ice, which allows the water to flow uphill and to deposit sediment going uphill. So this is one that ascends the valley and then sort of comes back down into it. There are also examples where they actively exit the valleys over the valley sides. And this is really hard to explain. We haven't yet come up with an adequate explanation for this under that alternative inverted fluvio-paleochannel hypothesis. So we think these are probably more likely to be Eskers. But we're still obviously testing this with the morphometries that Aaron Wild is doing for his master's project. And this is just a nice comparison that Rob Storer pointed out to me. So this is a sinuous ridge in Chucken Crater. As you can see, it ascends this valley wall and then comes back down into the valley again. And I think this comparison is quite stark. Here is an Esker in Finland within a meltwater corridor, which does not comply to the topography of the valley itself. It crosses this wall here and then comes back down. And I think they're so remarkably similar. I just wanted to share this with you, right down to this little wiggle here that we have in both systems. Now, just for honesty's sake, I do implore you to look at the scale bar here. They are on slightly different scales, but I think that's quite a fascinating comparison. So we're looking for Eskers elsewhere on Mars, and we're doing all right at it at the moment. We're finding candidates elsewhere, both in Tempa Terra and in other regions. So watch this space for some new identifications of Candida eskers. But obviously the elephant in the room is that glaciers, when they produce meltwater, don't always produce eskers. So the last kind of piece of science I wanted to share with you today is this piece of work led by one of my other PhD supervisors, Susan Conway, which was looking at glacial erosion rather than glacial deposition. So this is a bit of a complex story, but I'm going to try and summarize it very quickly, if I've still got your attention. So Susan's focus is on sloped processes on Mars, and her first love, shall we say, for Mars was gullies and debris flows on Mars. Gullies being these features that comprise alcoves, transportation chutes, and depositional fans. Now, in the present day, it's thought they're probably, this erosion of gullies is probably carbon dioxide frost sublimation driven. But there are also arguments for further back in the past them being formed by liquid water. So that's still an ongoing debate, but it's probably a combination of both processes over time. Now, one of the things that Susan and also a colleague, Challing de Haas at Utrecht, and others identified was that gullies on Mars don't seem to, the sizes of the alcoves of gullies don't seem to correlate with the age of the impact craters that they are in. Steep slopes and impact craters have always been around on Mars. So you would expect that gullies would have been growing over Mars's entire history. However, it seems that there's no correlation with age. So it seems like the gullies might all be of a similar age. And that suggests that older gullies from previous times might have been erased. And the slopes reset, and then new gullies incised, and then they've started to grow, and they've all obviously got similar alcove morphometries. What Susan identified after many years of staring at gullies, and I'm pretty impressed by this whole assemblage, is that where you have gullies associated with what you've probably spotted down here, which is glacial ice or moraines. So here is some glacial ice that's been pushed into the crater by what we think was a crater wall glacier forming a moraine feature here. Where they are associated with these deposits, they also are associated with heavily eroded crater walls. So we call it texturally altered bedrock, which we basically call mashed up bedrock. It's very smooth. And it contrasts markedly with facing unglaciated walls. So this is the glaciated wall here, and the crater floor glacier is here, but there was probably a glacier on the rim here. But the facing wall here has not experienced glaciation and has a very fresh morphology, which is over here in this panel, panel E. And you can see the difference between panel E here and panel D. And not only is it texturally different, the slopes of the crater are asymmetric, and this slope has been much more heavily eroded than this slope. And so Susan did lots of measurements of the slopes of these crater walls and found through some calculations of erosion that the erosion of these crater walls seems to be similar to the rate you would expect from wet-based glaciers. So this is a hypothesis that's ongoing. But we're not suggesting that these glaciers were pouring tons of meltwater out the front. It could have just been pore water, small amounts of meltwater allowing this erosion to happen. But yeah, this assemblage I think is just remarkable. So I wanted to show it to you, this moraine down here, and this potentially glacially eroded alcove. So potentially we had high rates of erosion on these crater walls. So yeah, we're not just confined to looking at Eskers, but also thinking about other possible markers of wet-based glaciation on Mars. And with that, I'll leave you my summary slide because my voice is slowly dying. So we have an emerging view of rare localized wet-based glaciation on Mars within the last few 100 million years, which is recent for Mars. That melting was probably driven by geothermal heating and strain heating in combination. Our analyses of Esker morphometries on Mars are helping to understand the possible dynamics of the melt events that form them and to search for Eskers elsewhere on Mars. And we found more glacier-linked candidate eskers in Temperatura and beyond, so watch this space for papers on that. And before I stop talking, I would like to draw your attention to next week's seminar, which is back on a Wednesday again, by Christine Dow. I hope I pronounced your surname correctly, Christine. On the role of Antarctic subglacial hydrology in ice dynamics and stability. So that looks like it's going to be a fascinating talk. And with that, I think I will take any questions.
Well, thank you very much. What amazing data.
That's always the reaction.
Plants really get in the way, don't they?
Yes.
On Earth. So questions, if you'd like to ask a question, if you just type yes into the chat, we will find you and unmute you, and you can ask a question. Perhaps while people are thinking, I'll ask you if you have an idea of how thick the glaciers on Mars might be.
So in the present day, so we have ground penetrating radar, which I didn't have time to show. I would have liked to have had time to show. So the little valley confined ones are probably quite thin in the present day, but the thick sort of Piedmont style ones, for example, have the basal interfaces have been seen in radar, and they are up to hundreds of meters thick, so 300, 400 meters thick in the present day. There is evidence for much thicker ice in the past, so there are sort of two hypotheses for this recent glaciation, either that it was in the sort of style that we see in the present day, which is these hundreds of meters thick sort of mountain style glaciation, or that they are actually remnants of much thicker, much more extensive ice cap style glaciation that's thinned, and then they've become debris covered valley glaciers as their sort of remnant form. But in the present day, yes, up to hundreds of meters thick.
Okay, fantastic. Jack, you are unmuted.
Yeah, I was just going to ask about the Eskers. That implies that the glaciers have retreated, and are the Eskers covered then with a 10-meter layer of the covering material that otherwise covers the glaciers?
So we don't know, obviously, but it doesn't look like they've got like debris. They look like just Eskers as you would see on Earth. I should say that one of the aspects of that sort of two-side hypothesis between was it mountain glaciation or were they much thicker sort of ice caps that have retreated into mountain glaciation, if it is the ice cap style glaciation, when it was glacial maximum, they probably weren't debris covered. And then as they've retreated into the valleys, they've then become debris covered. Now the debris could be debris, or it could be dust from the atmosphere, or a combination of both. But yeah, it looks like they're pretty exposed Eskers.
Quick follow-up is, are there terminal moraines then associated with that anywhere where the Eskers?
Not as far as at the terminus of that Esker that I showed you. So we think these are probably transient wet-based events. We don't think they were sufficiently long-term to also form moraines. However, we do see moraines on Mars. They're quite common among the sort of smaller, surrounding the sort of smaller valley-style glaciers. So moraines, quite substantial moraines, do exist, but not so substantial with the Eskers. We do see things that could be like aprons that were at the terminus of the cold-based glacier when they were more extensive, certainly in Temperatura, but not sort of constructive moraine systems.
So there's a question on the chat from Andre, who I can't unmute for some reason, but asking how the low gravity might affect the morphology of the Eskers and other forms.
This is a question I forever ask myself. So obviously gravity makes things flow slower, and also has all sorts of effects on geomorphology. So this is actually a question that we're actively looking at with Esker sedimentation modelling, varying gravity. So watch this space for that. We think that it could potentially explain why Eskers on Mars are much wider than Eskers on Earth relative to their heights. But yeah, we're working on that.
Thank you.
Anyone else for a question?
Oh, Stephen Bruff has a question.
You're unmuted, Stephen.
Thanks. Hi, Francis.
Hello.
For your northern hemisphere, then, the crater that you were talking about with these new candidate Eskers, perhaps, I guess, to some more uninitiated, you might also point or talk a little bit about that kind of dichotomy that you've mentioned a few times of pole facing. Because I was thinking, of course, here with the comparison in the southern hemisphere with the Hartmann paper in 2014 and Crater Greg, for example, where on the opposite side there's these lots of these viscous flow features, shall we say, and then on the other side of the crater, again, the more fluvial kind of nature. Now, naturally, the debate of the small Esker-like feature that Bryn identified on that kind of northern wall, again, I guess has some comparison. So is that a kind of
absolutely
thought about in the sense of, is because obviously that Greg probably has a lot less geothermal potential based on its locality. So again, if it's a different kind of setting, how might that play into that kind of analyses that you've had, or the hypotheses anyway, that these are kind of perhaps more tectonically location is crucial.
So I think as we accumulate more observations, certainly observations at more regional scales, I think it will become clear that it's not as simple as just some geothermal heat. I think if we start to accumulate observations over larger areas of potential wet-based glaciation, then we do need to start considering that the story might be more complex, as it always is with nature. But yes, as you say, there are other areas where there are sinuous ridges that look a bit like Eskers. I would say that the ones in Greg, as far as I know, don't actually come out of glaciers. And that's the big sticking point with identifying Eskers, is that you can be much more confident it's an Esker if it's coming out of a glacier. As soon as you remove the glacier, it becomes much harder to prove it's an Esker as opposed to something else. But certainly those ridges that you mentioned in Crater Greg are on my radar. And I think that it would be really interesting to do some morphometric comparisons with the ones that we've identified, for example, in Shukung. But basically, there are so many Eskers, or Esker candidates, to look at. And so I just haven't got around to it yet. But yes, they're certainly on the radar.
I think the one in Greg is that there's those longitudinal landforms actually inside that big moraine. Mm-hmm. They may be more useful from the sense of a wet-based perspective. Potentially.
So Stephen's mentioning there's a fascinating crater that's the focus of work in Aberystwyth in the southern hemisphere, where there's these smaller valley-like glaciers with moraines around them. And Bryn Hubbard published a paper identifying some really fascinating linear features within those moraines, but in front of what's interpreted as the retreated ice. However, they're much smaller, I think, in scale than lineations that you would see, like drumlins and megascale glacial lineations that you would see on Earth. So, yeah, but they're certainly fascinating for looking at further.
Thanks.
Frank, you had a question?
Yes. Well, you were showing, it was a very interesting talk. You were showing temperate or so, yeah, meltwater possible underneath these glaciers. But what about the polar caps? Does then the strain heating would also imply that you could have substantial, or could have actually, or in the past, have had subglacial melting underneath the polar caps on Mars?
Mm-hmm. So I actually deleted those slides because my talk was too long, but you've hit on a good point. So the simple answer is that the polar caps are actually thought to be much younger than the present-day glaciers in the mid-latitudes. The polar caps, sort of the substantial ice thickness, may be only a few million years old, maybe 5-10 million years old. And there hasn't been an identification of sort of proper glacial flow in those polar caps. And and it's also very, very, very cold at the pole. So the basal temperature, I think, in the present day at the South Pole has been modelled to be 162 Kelvin or something. And so it's thought that strain heating probably isn't particularly important in that location. However, in 2018, there was an identification by an Italian team using the Mars Express orbiter ground penetrating radar called MARSIS of a bright reflector at the base of the South Polar ice cap, which they found to be most consistent with a patch of water, so either a lake or muddy sediment. And that reflector was about 20 kilometers in diameter. So they suggest that there is actually a South Polar subglacial lake in the present day. And since then, there's been some modelling by Mike Storer and Ali Bramson in the US, but also by Neil Arnold, who did the 1D modelling for this study. And that has shown that basically without salt at the bed of the ice and without a geothermal heat anomaly within the last few million years that's still sort of cooling down, you can't explain that as a lake without those conditions. So, and Neil's modelling showed that it can't be caused just by generic extensive wet-based glaciation, because the flow routing that he's modelled does not predict a lake at that location. It's actually between lakes that would be predicted from extensive basal melting just from hydraulic potential. And so the modelling suggests that if it is a lake, then it's probably some kind of patch of water that's dammed by cold-based ice, and so that would be consistent with the geothermal heat anomaly. And that's sort of the same kind of implication that the American team have found as well. So yeah, potentially subglacial water beneath the South Polar cap in the present day, but I don't think strain heating would be important in that case because we don't think they're really flowing.
Thanks a lot.
So a question from Alexander Gross. Why are crater-filled glaciers the most common glacier type on Mars? I don't know if you want to add to that, Alexander.
No, I'll just go ahead then. Craters are really common on Mars, so so basically you get glaciers where the setting allows it. So the craters are pretty ubiquitous, and so you do get a lot of crater filling. And yeah, they're really fascinating. One of the things that's quite interesting is that the other subtypes are quite sort of patchy throughout the mid-latitudes, but the crater ones seem to be pretty ubiquitous. Now that's partially to do with the availability of topography. Craters create topography in some otherwise quite flat areas. So yeah, they're really fascinating. And it's not just crater filling glaciers, there's also these crater wall glaciers like the ones that Stephen was talking about in Crater Greg as well.
Any last questions, or has the discussion reached an end there? I think that's probably the end. Oh, yeah, I think that's the end of the questions. So I think that leaves us to say thank you very much from all of us for a really fascinating talk. Amazing graphics.
Well, I can thank Sean Duran for most of the graphics.
Brilliant. And to see everyone next